Good morning, students. Myself, Vijay Shankar from Electronics and Communication Engineering Department, Chopra Engineering College. Today, we are going to discuss about the Fourier transform. Fourier transform. In the previous classes, we already discussed about the Fourier series and what is the relation between of Fourier series and the Fourier transform. So, let us first of all, you can see what is a Fourier transform. Okay. So the Fourier transform in Fourier series, any continuous time periodic signal, in Fourier series, any continuous time periodic signal f of t can be represented as linear combination of complex exponentials and Fourier coefficients or discrete. The Fourier series can be applied to periodic signals only. Remember here, my dear students. See, the Fourier series can be applied to periodic signals only. This is very important. But the Fourier transform can also be applied to non-periodic functions. See, we already discussed about the Fourier series. The Fourier series can be applied to periodic signals only. Periodic signals only. But coming to the Fourier transform can also be applied for non-periodic functions. Means it is applicable for periodic and also the non-periodic signals or the functions like rectangular pulse, step-in, ramp, etc. Okay. The Fourier transform can be developed by finding the Fourier series of the periodic function and then tending t to infinite. Tending to t to infinite. If t tends to infinite, then f of t becomes a periodic signal. If t tends to infinite, then f of t becomes a periodic signal. So always in the periodic signals means within the limitations of 0 to pi or the 0 to 2 pi or 0 to 0.5 or 0 to 1. With this period, if the signal is repeated, we can call it as a periodic signal. But if that time period tends to infinite, then that f of t, nothing but that signal becomes a periodic signal. That signal becomes a periodic signal, or it is also called as non-periodic signal. Non-periodic signal. So once again, so what is the Fourier series and what is a Fourier transform? Fourier series can be applied to periodic signals only. But the Fourier transform can also be applied to non-periodic functions like rectangular pulse, step-in, ramp, etc. The Fourier transform can be developed by finding the Fourier series of periodic function and then tending this t to infinity. If that t tends to infinite, then the f of t becomes a periodic signals. So you can analyze the signal, either it is a periodic and non-periodic, by using the Fourier transform. But Fourier series can applicable or applied to periodic signals only. So now, deriving the Fourier transform from the Fourier series. Deriving the Fourier transform from the Fourier series. So what is a Fourier series here? The Fourier series, exponential Fourier series. What is the exponential Fourier series? We know the x of t as a synthesis equation. X of t is equal to sum of k equal to minus infinite to infinite x of k e power, here the positive, e power j k omega naught t, j k omega naught t. Here they are taking as a x of t as a f of t, as x of k is f of n, and the k, instead of k value, they are taking here the n. Okay, so whenever the n is there, the exponential also it shows e power j k instead, it is a j n. Nothing is different. Okay, and this is a analysis synthesis equation. Now coming to the analysis equation, x of k is equal to what we know. The x of k is equal to 1 by t, the integral t. When the x of k is a coefficient, the signal is there, x of t into e power minus j k omega naught t. The analysis equation. Here they are using the, instead of x of k is a f of n, f suffix n, f of t is a signal, and the variable k, and here the t. The k is in the n and the t is the same. Following my students. So don't confuse here. So for this signal f of n, I am converting or cross multiplying here, the t f n is equal to integral minus t by 2, the t by 2 I am taking as aperiodic signals. Aperiodic signal. What I said here, if t tends to infinity, then f of t becomes aperiodic signal. So I am changing the finite duration, the minus t by 2, the t by 2 as a minus infinite to infinite as of aperiodic signal or the non-periodic signal, f of t e power minus j n omega naught t dt. All right. So here the f of omega is equal to f of omega. See, whenever it is a x of k, the symbol is always for the Fourier series. X of omega. Omega means it is a Fourier transform coefficient. So f of omega is equal to integral minus infinite to infinite f of t e power minus j omega into dt. Omega into dt. These are equation to find the Fourier transform of the given signal f of t. What is the difference for these two functions? The coefficient fn becomes, comparing with the 1 and 2 equations, tfn is equal to f of omega. Fn is equal to 1 by t f of omega. Okay, and the omega, what is the omega here? N into omega naught. So in a continuous, omega is equal to n omega naught is a discrete. Follow my dear students. So now the f of t becomes, what is the f of t? F of t becomes sum of n is equal to minus infinite to infinite. Instead of fn, we have the fn is here. Fn 1 by t f of omega e power jn omega naught t. Jn omega naught t. Understood, my dear students? The Fourier transformation and the Fourier series relation is, as a omega continuous here, that becomes of n into omega naught as a discrete functions. And the tfn is becomes of f of omega as a coefficient. Now what is the formula for the Fourier transformation? F of omega is equal to integral minus infinite to infinite f of t e power minus j omega t into dt. E power minus j omega t dt. Total function n into omega naught is becomes here, it is a omega 1. Okay. Now, the f of t, the sum of n is equal to minus infinite to infinite 1 by t. and this equation 1 by t f of omega e power j n omega naught t. I substitute the fn is equal to, here this fn is equal to 1 by t f of omega, and 1 by t the sum of n is equal to minus infinite to infinite f of n omega naught t and e power j n omega naught t. And n omega naught t and n omega naught t, you can convert it as a omega as a discrete functions to the continuous function. F of t is equal to 1 by t. The 1 by t means in terms of the angular frequency, omega naught is equal to 2 pi f actually, 2 pi by t, where t is equal to 2 pi by omega naught. You can substitute in the 1 by t, it becomes of omega naught by 2 pi. Okay, as n tends to infinite, n omega naught approaches as a continuous frequency variable omega. Continuous frequency variable as omega. See, the omega naught is equal to omega by n. By n omega naught is equal to, I'm taking case of omega. So n cross multiplying the n into d omega naught, n d omega naught, apply the derivative on both sides, replace this n d omega naught is equal to d omega. As a summation, it becomes here the integral values. Why it is the integral value? It is the inverse Fourier transform the equation. F of t is equal to 1 by 2 pi, the integral minus infinite to infinite f of omega e power plus, this is becomes of the plus e power j omega t d omega. J omega t d omega. For the periodic signals, a discrete waveform is formed, and for the aperiodic signals, continuous waveform is a form. The Fourier transform of the signal f of t is defined as is a signal f of omega is equal to integral minus infinite to infinite f of t e power minus j omega t dt. And inverse Fourier transform is the f of t is output here. F of t is equal to 1 by 2 pi, the integral minus infinite to infinite f of omega e power j omega t d omega. You see here, it is with respect to the omega in the inverse Fourier transform. It is with respect to the time in the Fourier transform. Following my dear students. And in the f of omega, if it having the magnitude and the phase, the magnitude of f of omega and e power j theta omega. So I know the z is equal to r into e power j theta. R is a magnitude and e power j theta is a phase angle. Theta is a phase angle, and this is a magnitude, and e power j theta omega is a phase. By application of the Fourier transform, a signal is time domain is converted into the frequency domain. Means f of omega is a frequency. F of omega is a frequency, and the f of t is a, not the f of t is a small f of t is a time. So converting the time domain function to the frequency domain by applying the Fourier transform to the signal f of t. The application of the Fourier transform is signal in time domain. So the signal in the time domain is converted into frequency domain. Converted into the frequency domain. See again. See the Fourier transform, the periodic signals which extended over the interval, the periodic signals which extend over the interval minus infinite to infinite can be effectively represented with the help of Fourier series. So actually the Fourier series is a periodic signal with a period of minus t by to the t by 2 or 0 to t, or it is a minus t to the t. Follow my students. But in the Fourier transform, the periodic signals which extend over the interval minus infinite to infinite can be effectively represented with the help of Fourier series. A periodic signal which are strictly time limited can also be represented by Fourier series. See, the Fourier series is only for the periodic signals. A periodic signals which are strictly time limited. Remember here, my dear students. A periodic signals which are strictly time limited can also be represented by the Fourier series. A time limited signal means it has zero value outside the specified interval, and asymptotically time limited means as time approaches to infinite. As time approaches to infinity, the value of signal becomes 0. That is, x of t tends to 0 as t tends to infinite. X of t tends to 0 as t tends to infinite. Such time limited signals can be more conveniently represented by Fourier transform. Such time limited signals can be more conveniently represented by Fourier transform. In frequency domain, these signals are aperiodic because their period is t naught tends to infinity. T naught tends to infinity. Follow my dear students. Now you can see here the Fourier transform is a periodic signal which extended over the interval minus infinite to infinite can be effectively represented with the help of Fourier series. A periodic signals which are strictly time limited can also be represented by Fourier series. A time limited signal means it has a zero value outside the specified interval. Outside the specified interval. And asymptotically, time limited means as time approaches to infinity, the value of signal becomes 0. That is, x of t tends to 0 as the t tends to infinite. As the time is infinite, the signal x of t tends to 0. Such time limited signals can be more conveniently represented by Fourier transform in frequency domain. And these signals are aperiodic because their period to infinite. So see, the Fourier transform can also be found for periodic signals. It provides effective reversible transformation link between frequency domain and the time domain representation of the signal. Actually, in the Fourier series, the reverse, nothing but there is no any inverse Fourier transformation. We are calling it as the analysis equation and the synthesis equation. Analysis equation and the synthesis equation, my dear students. But in Fourier transform can also be found for the periodic signals, and for the periodic signals it provides effective reversible transformation link between frequency domain and the time domain representation of the signal. We have seen previously that for non-periodic signals t tends to infinity, as a period of signal t tends to infinite, the frequency becomes 0 because inversely proportional to the time and the frequency. If time is to infinity means the frequency is 0. Therefore, the spacing between the spectral components becomes see here there's something is missed here, as the frequency spectrum appears as to be the continuous, whereas the periodic signals has a fixed period t naught. Fixed period t naught. Actually, it becomes of a infinite. Therefore, their frequency spectrum is discontinuous, as we have seen in the examples of the last section. See, it is not that much important here. See, once again, I have to explain here, the Fourier transform can also be found for periodic signals. It provides effective reversible transformation link between frequency domain and time domain representation of the signal. Means the x of t, apply the Fourier transformation, get the x of omega. So inverse Fourier transformation means it is a bidirectional. X of omega is equal to in terms of x of t. It is effective reversible transformation link between the frequency domain and the time domain. Is a time domain x of t and x of omega is a frequency domain. And we have seen the previously that the non-periodic signals at t naught tends to infinity. A non-periodic means it is not having a particular time interval, and the t tends to the infinity. It is a non-periodic signal. As a period of t naught is tends to infinity, the frequency becomes 0. The frequency becomes 0. Now coming to the definition of the Fourier transformation, you see, already we've seen x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt, or you can substitute here in terms of the frequency, the omega is equal to 2 pi f, substitute x of 2 pi f here, minus infinite to infinite x of t e power j, omega is at 2 pi f into t dt. So the shortcut notation of x of 2 pi f is equal to x of f only. So both are the same representation. It is angular frequency and it is a normal frequency, the Fourier transformation. X of f is equal to minus infinite to infinite x of t e power minus j 2 pi f into t dt, means changing of omega as a 2 pi f angular frequency. Okay. And similarly, the x of t can be recovered from its Fourier transform of x of f by using the inverse Fourier transform. By using the inverse Fourier transform. What is the inverse Fourier transform? Previously, we derived the expression from the Fourier series. Inverse Fourier transform is x of t is equal to 1 by 2 pi integral minus infinite to infinite. Now it is x of omega as an input, e power plus j omega t d omega, and this integral is with respect to the omega, my dear students. Okay, by using the angular frequency and by using the normal frequency, You see the omega is equal to, we know the 2 pi f. Omega is equal to 2 pi f. Apply the derivative on both sides. D omega is equal to 2 pi into df. Okay, my dear friends. Now this equation becomes of x of t is equal to 1 by 2 pi integral minus infinite to infinite x of omega, it becomes of 2 pi f and e power j, the omega becomes 2 pi f into t here, t. And what is a d omega? D omega is equal to 2 pi into df. Okay, my dear friends. I substituted the d omega as 2 pi into df. So here the 2 pi is there and here the 2 pi get cancelled. X of t becomes of x of t is equal to integral minus infinite to infinite x of 2 pi f. The shortcut notation is x of f e power j 2 pi f into t df. So inverse Fourier transformation in normal frequency, the same signal here. See the x of t is equal to integral minus infinite to infinite x of f e power j 2 pi f into df. And 2 pi get cancelled after applying the derivative of omega. So inverse Fourier transform and the Fourier transformation. It is effectively reversible. Understood, my dear students? So the Fourier transform can also be found for the V dot eq signals. It provides effective reversible transform link between frequency domain and the time domain representation. So x of omega is equal to integral minus infinite to infinite x of t power minus j omega t dt is a Fourier transform of the given signal x of t. And inverse Fourier transform of x of omega, the x of t is equal to 1 by 2 pi integral minus infinite to infinite x of omega e power plus j omega t d omega. See now the pairs, the Fourier transform pairs, the functions x of t and x of f form a Fourier transform pair. Form a Fourier transform pair is written by a shorthand symbol shown x of t is a Fourier transform, is a bidirectional x of f, or x of f is equal to, when I am using the f is equal to, you can write this as a Fourier transform of f of x of t. So relation is actually the x of t, the Fourier transform x of omega or x of f. Or when I am using the is equal to, x of f is equal to, it is a Fourier transform of the x of t signal. Okay, or otherwise x of t is equal to, when I am using the x of t as an inverse Fourier transformation, inverse Fourier transform of x of f is a relation actually. X of t is equal to inverse Fourier transform of x of f inverse or f, or you can use it as a Fourier transformation, inverse Fourier transformation or the f inverse. This is a shorthand notation of the Fourier transform pairs. These are pair actually, the x of t and x of f, and this x of f is equal to the Fourier transform of x of t, and x of t is equal to inverse Fourier transformation of the x of f. Okay. Now, in the block diagram representation is a linear operator. Fourier transform, this can be considered as a linear operator. X of t, you can given the signal, apply the Fourier transform. See here the f. Apply the Fourier transform of the input signal x of t, you'll get x of f. When we can take the x of f frequency domain signal, apply the inverse Fourier transform, getting of the signal x of t, time domain function. Means time domain function is converted into the frequency domain function. By using the inverse Fourier transformation, frequency domain function is converted into the time domain function. Following my dear students. Coming to the Fourier transformation purpose. The purpose of the Fourier transformation, it is a non-periodic signals can be represented with the help of Fourier transform. It is a very, very important, my dear students. This point is for non-periodic signals can be represented with the help of Fourier transform. See, the periodic signal can be represented with the help of the Fourier series. And Fourier transform provides effective reversible link between frequency domain and the time domain representation of the signal. There is effective representation of the signal between the frequency and the time domain. Between the frequency and the time domain, my dear students. For non-periodic signals, T0 tends to infinity. Definitely, if the t tends to infinity, means it is a non-periodic. Remember that one. If t tends to infinity, it's a signal, periodic signal becomes a non-periodic signal. Hence, what is the frequency at the time? Is a 0. Because if t is equal to infinite, means f is equal to 1 by t. So that is equal to 1 by infinite. What is the 1 by infinite? Nothing but the 0 one. Okay. Frequency is a 0. Therefore, the spacing between the spectral components becomes infinitesimal. This is the missing term is there in the previously, my dear students. You see here, infinite. Okay. And hence, the spectrum appears to be continuous. And hence the spectrum appears to be continuous. Okay. Now, again, the definition you can see, the definition of the Fourier transform is x of omega is equal to minus infinite to infinite, x of t e power minus j omega t dt, or in the normal frequency, x of f is equal to integral minus infinite to infinite, x of t e power minus j 2 pi f into dt. In the Fourier transform, the exponential is a negative exponential, my dear students. Here x of t is a time domain representation of the signal, and x of omega and x of omega is a frequency domain representation of the signal with the frequency omega. Sometimes x of omega is also written as x of j omega. X of omega can also be written as x of j omega. Why it is, it will get in the after the Laplace transformation. And similarly, x of t can be obtained from x of omega by inverse Fourier transformation. What is the inverse Fourier transformation formula? X of t is equal to 1 by 2 pi integral minus infinite to infinite x of omega plus, here the exponential is a positive, my dear students, e power j omega t d omega, or in the normal frequency, integral minus infinite to infinite x of omega, it is not the minus, my dear students, it is a plus. X of omega e power plus j 2 pi f into t df. And the Fourier transform pays x of t, the Fourier transform of x of omega, or x of t, the Fourier transformation is x of f, normal frequency and the angular frequency. Okay. Now, the discrete conditions, whatever we discussed in the Fourier series, and here also the extension of existence of the Fourier transform, discrete conditions. The following conditions should be satisfied by the following x of t of the Fourier transform to exist. Already we know the single valued property, finite discontinuities, finite peaks, and absolutely integrable for the Fourier series. And here also the x of t must have only value at any time instant over a finite time interval, the t. The same thing, x of t should have at the most finite number of discontinuities over a finite time interval t. And over a time interval t, the x of t should have finite number of maximum and the minimum. And it is also the absolutely integrable of x of t signal. Integral minus infinite x of t is less than the infinite after applying the integral with respect to the time. And here, whatever the conditions we have, that conditions are sufficient, but it is not necessary for a signal to be Fourier transformable. Okay, and these conditions are sufficient, but it is not necessary. These conditions are sufficient, but not necessary for a signal to be Fourier transformable. So already we explained with the graphical representation also, when we can call it as a single valued property, and the finite discontinuities, and finite peaks, and absolutely integrable. And these are all having with the over a finite time interval t, and these conditions are sufficient but not necessary for the signal to be a Fourier transformable. In the Fourier transform, simply saying. Coming to the Fourier transform properties. See, I already told in the Fourier series, Fourier transform, Laplace transform, and the Z transform. All these three transformations, not it is a Fourier series is not the transform, but the Fourier transform, Laplace transform, and the Z transform is the transformations converting of time domain to the frequency domain functions. As t tends to infinite, the signal is a periodic signal, and at that time the frequency is a zero. So whatever the properties we already discussed in the Fourier series, the same in the Fourier transform also. But the equation is a difference here, my dear students. Don't confuse. If they ask in the Fourier transform, you can only prove that in the Fourier transform. If they ask in the Fourier series, you have to prove that in the Fourier series equation only by using. So the same thing in the Fourier series and the Fourier transform. Whatever we discussed in the linearity property, time shift property, frequency shift property. Understood? See the first property, the linearity property. First property is a linearity property. What is the difference in the linearity property for the Fourier transform and the Fourier series, my dear students here? Actually, in the linearity, the statement saying in the Fourier series is x of t is a Fourier series. X of k means y of t as a Fourier series y of k. Okay, but you have to prove that z of t is equal to a into x of t plus b into y of t is a Fourier series. I'm writing is a Fourier series statement, my dear students. Because what is the difference here, the Fourier transform and the Fourier series? Z of k is equal to, see the k, what we are representing the k here, that is for Fourier series, omega is for Fourier transform, and later we can discuss about the Laplace. S is a Fourier Laplace transformation and Z is a Z transformation. X of k is for the Fourier series. X of omega is Fourier transform. X of S is a Laplace transform. X of z is Z transformation. This is a symbol represented for the Fourier series, Fourier transformation, and the Fourier Laplace transformation, and the Z transformation. Here the K is we are using for the Fourier series. What is the Z of K here? A into X of K plus B into Y of K. This is a statement for the Fourier series. See here, for the properties of the Fourier transformation, the linearity property is also saying the same thing. X of t, the Fourier transformation is X of omega, since it is we are applying the Fourier transformation. And Y of t, the Fourier transformation is Y of omega, since we are applying the Fourier transformation. Then, what is the Z of t? The same thing. A into X of t plus B into Y of t. Applying the Fourier transformation to get Z of omega is equal to, why it is a Z of omega? We are applying the Fourier transformation. Z of omega is equal to A into X of omega plus B into Y of omega. Instead of X of K and Y of K, Z of K is now the Z of omega, X of omega, and the Y of omega. In the exam point of view, they asked write the property of Fourier transform, linearity property of the Fourier transformation. If they ask, if you write it is X of K, it is a right for the Fourier series, but it is a wrong one where for the Fourier transformation, my dear students. Okay. Now the proof, we can see the Z of omega is equal to, what is the formula here? For the Z of omega, X of omega is equal to, it's a Fourier transformation formula, the integral minus infinite to infinite. Since it is a non-periodic signals, Z of t e power minus j omega t dt, j omega t dt. Understood? So integral minus infinite to infinite. What is the Z of t given? A into X of t plus B into Y of t. E power minus j omega t dt. And take the A, split the two parts as a into integral minus infinite to infinite X of t. This exponential is also multiplied with e power minus j omega t dt. Plus, take the common as a b here. And integral minus infinite to infinite Y of t e power minus j omega t dt. And again, this is the equation similar to of X of omega is equal to is X of t. X of omega is equal to X of t e power minus j omega t dt as X of omega. And here also the same thing, instead of X of t, the Y of t, you can write as Y of omega. Okay. Now Z of omega is equal to A into X of omega and B into Y of omega. What we have, it is the same. Coming to the time shift property. Time shift property. So see, I will explain in the whiteboard. What is the statement? X of t minus t naught. Here also the same thing, e power minus j omega t naught is multiplied for the X of omega. There it is, e power minus j k omega naught t naught into X of k. Now you can see. We'll take the second property, time shift property. Time shift property for Fourier transform. Okay, what is the statement here? Statement, if X of t is a Fourier transform X of omega, okay, then Okay, take it as x of t minus t naught as z of t is equal to, and what is the Fourier transformation of applying the x of t minus t naught is e power minus j omega t naught into x of omega. You have to prove. I am taking the proof here. We know z of omega is equal to the formula for the Fourier transformation, integral minus infinite to infinite as z of t e power minus j omega t dt. Okay, what is the z of t is given minus infinite to infinite x of t minus t naught e power minus j omega t dt. T minus t naught e power minus j omega t dt. Now here x of t minus t naught, I can assume the t minus t naught is a dummy variable. Let's assume t minus t naught is equal to m, and t naught is a constant here, the t is a variable and m is also variable. So apply the derivative on both sides, and dt is equal to dm. So now I can substitute here. If I am changing the dt as a dm, for dt the minus infinite to infinite means the dm is also the minus infinite to infinite. There is no change in the limitations. X of m and e power minus j omega, and what is the t here? T is equal to m plus t naught. M plus t naught. Okay. Into dt is a dm. Dt is dm, my dear students. Now the integral minus infinite to infinite, write all the m terms only. X of m e power minus j omega m dm, and another exponential is there, e power minus j omega t naught. Now see, within this parenthesis, it is an equation of similar to the top Fourier transform, integral minus infinite to infinite x of m e power minus j omega m into dm. Similar, it is x of omega 1. So e power minus j omega t naught x of omega. We got that when I was taking the z of t is equal to x of t minus t naught, after applying the Fourier transformation, you'll get z of omega is equal to e power minus j omega t naught into x of omega. And these two are the Fourier transformation bits. So for the time shift property, the time is shifted with the temples of t naught. Applying the Fourier transformation of this signal, you get the x of omega with negative exponential is multiplied, e power minus j omega into t naught. Okay. So see here, same thing. T minus t naught is there. As shift of t naught in the time domain is equivalent to introducing a phase shift of minus omega t naught, but amplitude remains the same. See, the time is changing means there is a changes occurs in the time only, but there is no any changes occurs in the amplitude because it's a time shifter. Time scaling, time shift, and the frequency shift also, there is a changes occurs in the time only. There is no any changes occurs in the amplitude. Amplitude remains the same. Okay. See now, instead of z, here they taken is a y of t. As a y of omega is equal to integral minus infinite to infinite y of t e power minus j omega t dt. What is the y of t here? X of t minus t naught as y of t minus t naught e power minus j omega t dt. E power minus j omega t dt. So actually it is a x minus 2x. assuming that, or put t minus t naught is equal to tau. We are taking the tau here. I taken it as a m. Tau, then t is equal to tau plus t naught. Apply the derivative on both sides. Considering as t naught is a constant, dt is equal to d tau, and integration limits really remains the same for dt and the d tau. So y of omega is equal to integral minus infinite to infinite y of tau, nothing but the t minus tau, t minus t naught, e power minus j omega tau plus t naught, as a t is equal to tau plus t naught. Then integral minus infinite to infinite y of tau, e power minus j omega tau and e power minus j omega t naught into d tau. Take all the tau terms in the one side, and e power minus j omega t naught, integral minus infinite to infinite y of tau e power minus j omega tau d tau. This total equation, integral minus infinite to infinite y of tau e power minus j omega tau d tau, is a y of omega. Y of omega. Following my students. So the same thing what we have in the Fourier series also. What is the Fourier series saying? That x of t minus t naught, the Fourier series is e power minus j k omega into t naught x of k. Now for the Fourier transformation, x of t minus t naught is the Fourier transformation pair as e power minus j omega t naught. See here the k omega is becomes of the omega, changing of the Fourier transformation represented by using the Fourier series. Same thing. Instead of x of k, here the x of omega. Symbol is different. It's for the Fourier series and is for the Fourier transformation. Nothing is a difference. Okay. So coming to the frequency shift property. Frequency shift property is also the same one. Okay. What in the Fourier series they are saying? The x of k minus k naught for the signal, the Fourier series e power not the minus is a plus j k naught omega t x of t. For this signal, we can apply the Fourier series. There is a shifting occurs in the frequency with the samples of k naught. The samples of k naught, my dear students. E power j k naught omega into t x of t in Fourier series. But coming to the Fourier transformation, the statement is x of t is equal to Fourier transform of x of omega. Then you can take here the y of t is equal to e power j beta into t. So instead of k naught, here they are taking that as a beta. The beta times is shifted in the frequency into x of t. Y of omega is equal to x of omega minus beta. Okay, let us see in the whiteboard this one. Third one, frequency shift property. Frequency shift property. For Fourier transform, my dear students, remember that one, Fourier transformation. So what is the statement? If x of t, the Fourier transform x of omega, then y of t is equal to e power j beta into t x of t. Apply the Fourier transformation of this signal to get y of omega is equal to x of omega minus beta. Actually, it is a k minus k naught in the Fourier series because the k is the symbol for the Fourier series. And the proof. So what is the omega? Y of omega is equal to y of omega is equal to, according to the Fourier transformation definition, y of t e power minus j omega t dt. Now what is the y of t? You have to take minus infinity to infinity e power j beta into t x of t as a signal x of y of t is given e power minus j omega t dt. Okay. The integral minus infinite to infinite, write the x of t as a signal, and the two exponential signals base is the same, e power. What is a common term here? Take as minus j. I'm taking the omega here, minus beta into t dt. See the e power minus j omega t, minus j omega t, minus into minus is a plus, e power j omega beta into t. Now it is also the similar to the frequency Fourier transformation equation only. Y of omega is equal to integral minus infinite to infinite y of t e power minus j omega t dt. Here the omega in the frequency also output side the y of omega. Instead of omega here, the omega minus beta. Omega minus beta. And the signal is x of t. You can write it as x of omega minus beta. Y of omega is equal to. So here, y of omega is equal to x of omega minus beta. Frequency shift property. In the frequency, the x of omega is a frequency. There is a shifting occurs in the frequency only. With how many samples of beta samples? How we get this frequency shift? By multiply e power j omega t for the signal of x of t. Okay, my dear students. See here, same thing. Y of omega is equal. It states that by shifting the frequency by beta in frequency domain is equivalent to multiplying the time domain signal by e power j beta t. It states that by shifting the frequency by beta in frequency domain is equivalent to multiplying the time domain signal by e power j beta into t. So for the signal e power j beta 2 into the signal x of t, and take the x of t and both are same base and add the powers e power minus j omega minus beta into t dt as of x of t signal. Here omega instead of omega it is omega minus beta. So x of omega minus beta. Understood, my students? Now I will write the two equations. The time shift property, time shift. Time shift saying that x of t minus t naught. What is the Fourier transformation here? E power minus j omega into t naught. So the samples is shifted x of omega. But in the frequency shift, for the Fourier transformation, x of omega minus beta, there is a frequency shifted with the beta samples and is multiplied with the factor of e power j beta t for the signal x of t. See, if the time is shifted for the frequency domain signal is multiplied with a negative exponential e power j omega into t naught samples. If the frequency is shifted with the beta samples, the time domain signal x of t is multiplied with a positive exponential. Positive exponential. The same thing in the, these two are related to the Fourier transformation. Fourier transformation. What is a Fourier series? See, in the Fourier series, the time shift x of t minus t naught, time domain signal only. But here we are applying the Fourier series, not the Fourier transformation. So e power minus jk omega naught t naught. The samples is a t naught here, my dear students. So without confusion, don't write here the omega naught, it's omega only. And x of k. See here it is a similar t minus t naught, but as of a Fourier series, it is a e power j k omega naught into t naught. As a k omega here, it is a omega. X of omega is a frequency in the Fourier transformation. X of k is a frequency in the Fourier series. And frequency shift property, frequency shift. What is the frequency shift here? The frequency is shifted with the k naught samples, the frequency. X of k minus k naught. So in the frequency there is a shift occurs. For the signal x of t, can multiply a positive exponential j with the k naught samples, k naught omega into t. See, the k is becomes of k naught and the t naught t is a t only. Both are the same here. For Fourier series and the Fourier transformation, in the frequency there is a shifting occurs, means for the time domain signal, positive exponential is multiplied with the number of samples is shifted with the frequency, in the frequency shift. Similarly, in the time shift of Fourier transformation of the Fourier series, if the t naught samples is shifted in the time domain signal, in the frequency domain signal, the negative exponential is multiplied with the t naught samples. Understood, my dear students? So don't confuse. If they ask the Fourier linearity property, time shift property, or the frequency shift property in the Fourier series, you can write it in the Fourier series of the x of t. The same thing in the Laplace Fourier transformation, the linearity, the time shift, and the frequency shift. You can write it in the Fourier transformation with the x of omega. All right. Now, any questions? The introduction of the Fourier transformation and with the comparing or the deriving the Fourier transformation by using the Fourier series and the three properties of the Fourier transformation. Any doubts? Please rise. Okay, my dear students, thank you. Thank you, Anand.